Hi, today we're going to start Chapter 3, Modeling Distributions of Data, Day 1. So considering the following. A student gets a 78 on their exam. Oh, okay. A middle-aged man goes to the doctor and finds his cholesterol to be 210 milligrams per deciliter. An employee's salary is $42,000. A 10th grader scores a 46 on the PSATs. Great, but these are isolated numbers. Where do I stand? Are these good? Are these bad? Let's take a closer look. Where is the score of 78 in terms of the rest of the class? If the average of the class was a 72, then a 78 is a great score. I'm above average. But if the average of the class was a 92, then a 78 is a low score. We might have studied more. Okay, where's the average cholesterol? When looked at in context, a cholesterol of 210 is borderline high. So if I look at a table of cholesterol from the United States, below 200 is considered desirable. Between 200 and 240 is considered borderline high, and 240 and above is high. So 210 by itself, if I don't really know anything about cholesterol, doesn't tell me much. But if I know what level of cholesterol I'm looking for, I'm looking 210. Oh no, that's not a good number. That's a borderline high number. I want to do something to fix my cholesterol. A salary of $42,000. Is the employee on the higher end of the salaries or the lower end of the salaries? Is this employee a manager? Where does this salary stand amongst the others that have a job similar? I have no idea the answer to any of those questions, so I don't know if that's a good salary or not. A 46 on the PSATs. Out of what? What was the school average? What was the national average? How well did this student really do? So from a College Board, let's see, 46, we don't know if it's critical reading, math, or writing. I'm assuming based on this average here that it's only one of them, because if it was a 46 on the entire thing, then that would be a pretty low score. But if you got a 46 on the math or on the critical reading or the writing skills, then that would be a pretty high score, because look, it's above the average for all of the 10th graders there. Okay, we're not going to do this activity because we're not in class. So I have a pretend class here. Mrs. Navard's class data. So she went through and recorded the heights of each student in her class. So each dot is a student in the class. The dot on 62 right here means that this person is 62. There are 2 students that are 5 feet 2 inches tall in her class. There are 2 students who are 6 feet tall in her class. Okay, N means this is the number of students. The mean is the average. The standard deviation is how far away from average we are. The 5-number summary, the min, quartiles, median, quartile 3, and your maximum from Chapter 2. So Lynette is a student in the class. She is 65 inches tall. How many dots are below Lynette? Okay, so she is 65, so let's see where that is. Okay, she is 65, that's her right here. How many students are below Lynette? So I'm going to count 1, 2, 3, 4, 5, 6, 7, 8, 9 students, 10 if you include her. How many dots are in total? Well, it gives us this right here. We don't have to go and count them because it tells us there's 25 dots in total. What percent of dots or students are below Lynette? So we would do 10 out of 25. 10 divided by 25 is 0.4 or 40%. So we would say that Lynette is in the 40th percentile. 40% of students are shorter than Lynette. Okay, so let's define what a percentile is. Percentile is the pth percentile of the distribution is the value with p% of the observations less than or equal to it. There is an alternate definition. So let's read through this. It says the pth percentile of the distribution is the value with p% of the observations below it. So how are these different? What's the difference between the 2 definitions? So if I look really closely, everything word for word is the same except for this last little piece. The definition says less than or equal to. The alternate definition is below. Okay, so in general, percentile is data below. The only thing that differs between the two definitions is whether or not we're equal to or not. So quartile 1 is the 25th percentile. Quartile 2 is the 50th percentile because there's 25% in each part of the box and whiskers. So 100% of the data is represented by the box and whiskers. The quartile is the 25th percentile because from here and less is 25%. Quartile 2 is the 50th percentile because from this line and less is 25 plus 25. So what would the third quartile be? So start here and count less. That would be 25, 25, and 25. That would be the 75th percentile. Read the problem carefully. Sometimes it refers to the data above that percentile. So you kind of have to just make sure that you're reading and knowing what the question is asking you to do. All right, so for example, let's look at Mrs. Navard's class again. So same data as before. And what percentile are the 3 students who are 66 inches? So let's look at the different wordings of the definitions. Because there is different wordings, calculating percentile is not an exact science. So the first definition, it says less than or equal to. So if I go and count 66, there would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 dots that are less than or equal to, divide by the 25 dots total, puts me in the 52nd percentile. If I use the second definition, which just says below, then I'm not going to include these 3. So I only have 10 below out of 25 would give me the 40th percentile. But wait, there's another mishap right here. Do you see how 66 is the median number? So based on the quartiles, the second quartile is the 50th percentile. So all 3 of those answers would technically be correct. If I want to sound like I'm taller, then I will say that I'm in the 52nd percentile. Okay, if I want to be shorter, I'd say I was in the 40th percentile. Okay, that's why the statistics isn't an exact science, is because there is more than one definition. I'm going to use the definition that suits my purposes. All 3 of them are mathematically correct. Which one suits my purposes better? I should also say that the bigger this number is here, the bigger the total is, the less of a difference these will all be. So if I use a large sample, the difference between the percentiles will be very, very small. Okay. So how do we calculate percentile when we don't have the data to count how many observations are below a certain point? That's where we talk about where the value falls relative to the mean. Is it above or is it below average? We can describe how many standard deviations above or below the mean the observation is. So in a number line, if we put the mean in the middle, so if I do X bar, I can talk about 1 standard deviation below the mean. I could talk about 2 standard deviations below the mean, or I could talk about 3 standard deviations below the mean. Typically, because these are below, they're written as negative. They're not actually negative numbers. The data isn't actually negative. The negative sign just means below average. Or I can talk about 1 standard deviation above average, 2 standard deviations above average, and 3 standard deviations above average. Most data falls within 3 standard deviations above or below average. This process is known as standardizing. So remember the first thing that we did today was calculating the z-score? That's where this comes in. The z-score tells me how many standard deviations above or below average the data point is. So the x is our observation, the mean is the mu, and the standard deviation is the lowercase sigma. It looks like a circle with a line on top of it. So this is my average right here. So the mean is mu, the standard deviation is the lowercase sigma, and the observation is your x. All right, so for example, Lynette's height is 65 inches. What is her standardized height? So if we go and look and see, okay, so x is going to be 65. That's what we observe Lynette to be. The mean is given to us at 67. The standard deviation is given to us at 4.29. So if I plug those three numbers in, I get 65 minus 67 divided by 4.29. And my answer is negative 0.47. So if my average is 69, she should be below average. And look, 65 is less than 67, so she is below average. Lynette's height is 4.47 standard deviations below the class average. Okay, let's do another example. Brett's height is 74 inches. What's his standardized height? So the formula, x is what we observe Brett to be. The average is given to us at 67. So if I think about this, 74 is bigger than 67, so Brett should be above average for the class, and the standard deviation is 4.29. So if I plug those values in and subtract and then divide, I get 1.63. So Brett is 1.63 standard deviations above the class mean. All right, let's do another example. Sophia scores a 660 on the math test. The distribution of scores was single peaked with a mean of 500 and a standard deviation of 100. Jim takes the SAT and scores a 26 with a symmetrical distribution with mean 18 and standard deviation of 6. Who scored better on their exam? Well, right off the bat, it looks like 660 is bigger than 26. Does that mean Sophia scored better on her exam? No, because they were scored differently. I can't compare the two scores because they're on a different scale. However, I can standardize both and then compare the standardized scores. Because when I'm comparing the standardized scores, I'm looking to see where they stood in their grouping compared to their mean. So I can say if the z-score is bigger, then that person did better on their test than the other. All right, so let's do Sophia first. We have to go look for the information. Okay, the x value. What did we observe Sophia scored on her exam? We observed that Sophia scored a 660. What was the average on the SAT test? The average was the 500. What was the standard deviation? The standard deviation on that test was 100. So if I plug those values into the formula, 660 minus 500 divided by 100, I get a standard score of 1.6. And now we're going to do the same thing for Jim. Okay, so we have to go look. Jim scored a 26. We observed that Jim scored a 26. The mean on his distribution was an 18. And the standard deviation of the ACT was a 6. Plug those values in. That gives me 26 minus 18 divided by 6 is a z-score of a 1.33. So whose z-score is higher? Sophia's z-score is higher. So Sophia did better on the SAT than Jim did on the ACT because her standardized score was higher. Okay, email me or come see me for tutorials if you have any questions. There's some practice problems on 3.1 day 1 for you to do. I used page 105 to create the practice problems form. Guys, have a great day. Thank you.